Okay, now let's talk about vector spaces. What are these vector spaces? In the vector spaces you have these vectors and you have scalars, and these vectors and scalar need to follow some rule in vector addition and scalar multiplication. And the idea of this generalization is, if you find similar objects that follow same rule as these ordinary vector does, but they are in like higher dimension or all those things, you can apply those same rule, kind of the idea behind these vector spaces. So let's see what are these vector spaces. So in these vector spaces you have vectors. For example, you have a set of these vector and you have a set of these scalars. These need to be closed under two operations, vector addition and scalar multiplication. So when I say closed, it means that the operations we define on these vectors, these vector addition and scalar multiplication operations are well defined. By well defined, I mean that when I add two vectors, it's like if I am in three-dimensional space, it should not take me out of my three-dimensional space. It shouldn't just throw me in four-dimensional space. And if I'm multiplying the same thing, it should not throw me out of my vector space. And let's see what are these vector addition. You have already seen this. We're just gonna do it for the sake of completeness. So if I add two vectors, like if I add alpha plus beta, it should give me another vector. It should give me another vector which should also be inside the vector space. And the other next property is, if you add two vectors, in what order their adder shouldn't matter. And this is what known as commutative property. And if you're adding like three vectors, you could add first to first and then add with second, or you can add the last two and then add first. It shouldn't matter. And this is known as associative property. And there should be a null vector, where if you add a vector to a null vector, you should get a same vector as before. So, and every vector that is in the vector space should have a inverse vector. When you add a vector and its inverse, you should get 0. Yeah, so these are the rule under vector addition. And now let's let's repeat the rule then of scalar multiplication. Okay, so the first property is similar kind of thing. Like if you multiply a vector with a scalar, you should get another vector that is also in the vector space. And another one is the scalar multiplication is distributive. Scalar multiplication is distributive in both of these senses. If you multiply A with the addition of vector alpha and beta, you can distribute to alpha and beta. But then if you multiply two scalar, you add two scalars and you multiply with a vector, you can distribute that too. So it applies in kind of both of these way. And this is basically a distributive property. And the next one is associative. You can multiply B with the beta first, or either what you can do, you can multiply the scalars together first and then multiply with the beta, or you can multiply with A or then with B. All the things you can do, and this is known as associative, and this is known by associative property. And then kind of the same property that it should have, if you multiply with the scalar 0, you should get a 0 vector, and if you have and you multiply with the 1, it should leave your vector unchanged. Yeah, so these are the properties you kind of under this scalar multiplication and you have under vector addition. And the idea of this is when you generalize the this notion of ordinary vector and you find kind of similar objects in real spaces that follow the same kind of rule, you can apply the same knowledge as you have learned in ordinary vectors to these kind of systems you find in nature. And quantum mechanics is one kind of system. So I hope you like this video. If you do, give the thumbs up, like, share and subscribe. I will see you next time.